know, because some of us aren't good at keeping track of time.
You are alive.
I am, well, for now.
You have a pulse according to the voice meter.
Testing, testing, 1, 2, 3. Okay, I'm glad to hear it. Let's take this off the screen since it's probably not a good idea to have it up there.
No, we just brought guests out. It's fine.
We're good.
We did get trapped by copyright.
By, what did we violate?
With one of our sessions, one of my talks, because I had part of the projection of the SVFIG. And I had a period of silence where I was projecting a video that had no audio. And somebody has copyrighted that. A video with no audio?
You are extremely naughty. And we are, in order to make up for this, we're going to have to send you to our contractor in San Francisco, where you will be punished. Unless you like that sort of thing. In which case, we'll save ourselves a lot of money by not punishing you, which will.
What year was it copyrighted? Before silent movies?
No, somebody did this recently. And I guess they're going around. And I filed a objection that this is not copyrighted material. It's merely a video with no audio. And I haven't heard back.
And nor will you. That's one of the things I like about the city of Sunnyvale. I send them, you know, they have a web form for most of their departments of the government. The Star Chamber, not so much. And you send them a message, and damned if they don't respond.
Wow.
And you may not get what you want, but at least they acknowledge your existence.
Yes, yes.
So often I send an email. Good, John's not here. George isn't here. So often you send an email, and there are three things that normal email, yes, I understand that. Normal email participants should keep in mind. One is, you always respond. Two is, even if I can't get to that right away, but it's on my list of stuff, and I really will respond. And this is just to let you know that you're not going to hear from me right away, except for this.
Unless they're a recruiter.
And that has to be within 24 hours that you send something.
Unless they're a recruiter.
And the third thing is, if you're on the receiving end and you have communicated to somebody via email, to expect a response in less than 24 hours is unreasonable in the extreme. But those three things escape huge numbers of people.
3-minute warning. Yes. I frequently ignore recruiters.
Unless you're looking for work.
Even then, if it's Hillsborough, Oregon, no, I'm not there.
How do you know?
No, I'll do it right away. Probably got a signature. No problem. That's contract.
I guess maybe on our meetup announcement, I need to specifically say if you can't make it in person, join us on our Hangout on YouTube. You can go to the Hangout page and see. Although I looked at the Hangout page and it wasn't spectacularly clear. But I guess I shouldn't do that next month because Hangout's not going to work in September.
It will be something different.
Okay.
It will be something different. Brad assures me that it will be
Something.
equivalent.
There will be something.
No.
Something on the interwebs, but the claim is that it on the 12th it will transition to being something else.
Right, that it will be equivalent. Because people have scheduled events that they're going to just say, no transition.
It will be something wonderful. It's full of bugs.
But it will be wonderful. I hear skepticism.
Okay, just for fun, I'm going to write that onto our meetup page. Hopefully everybody will get with the program. It'll be on the agenda sort of. I will post the agenda sort of 20 minutes before the meeting starts in typical inadequate form.
The YouTube experience will probably be identical.
So all of the emails have been sent, the notices have been posted, the broadcast is live. I would like to welcome you to the afternoon August SVFIG meeting, those of you that are here in Corpus and those of you that are joining us on the internet. I have unfortunate news about Google Hangout, the method by which we are broadcasting and have broadcasted for some years now. Somebody was talking to me not a couple of months ago about a particular meeting, and I said, that was in what year? And I looked up on Google, and damned if there wasn't a Hangout. We've been doing this for quite a while now. And I'd like to thank Sam for getting us on the air with it, and Dennis for keeping the ball rolling for these many years. Thank you so much, gentlemen. And we're going to have something next month. We just don't know what it is. And wish us luck, and communicate on the email list if you can. If not, you know, get on the email list and communicate with us. If you've got a solution to this thing, I guess we'll see what pans out, and hopefully it'll all be happy. On this day in history, this was described on the radio, on the news yesterday as a bread truck. I don't know. Of all the things I would call that, you'd have to be really old to call that a bread truck. But there we were, August 27th, 1976. And this is a Wikipedia article. It's the packet radio van. This exact device, this exact van, with none of the guts, is actually sitting with a big canvas vehicle cover behind the Computer History Museum in Mountain View, even as we speak. Every once in a long while, they pull it out, maybe today, if you want to go down there right now. But you're here busy listening to us, so maybe put that off. But you can see a really good picture of it here in its shiny and new state with its antennas. But this was part of the big internet demo that is considered by many to be the start of the interwebs. Go figure. And it just goes to show you. In 1976, of all things, seems like it was only yesterday. All right.
You know, they call those bread trucks because they Wonder Bread used to use those type of style trucks for delivery. Way back in the early days.
Unfortunately.
Do you ever flip through your tabs and get to one that you don't remember opening?
That's the news ever.
Yeah.
We think it is.
Well, you have to hope that they.
You just see how we play with me, don't we?
You have to hope that they're not thinking.
They're hoping.
This is the gateway to Windows on the web. Windows in the cloud. Your Windows machine will be like a Chromebook.
Along with Bash on Ubuntu on Windows,
Wow.
which is now an app.
There's an app for that.
There's an app for that.
All right. So we're looking for volunteers to write the doorbell app. So you get to the door here at Stanford.
So it's Bluetooth compliant, it just rings it automatically.
Well, no, you bring up this app and you press the doorbell button and it rings the doorbell up in here.
Before I get to the door, it opens it.
Really?
You gotta hope. Either that or we'll put an image recognition camera
There you go. That's
and it'll open the door for you unless you're not Caucasian, much like HP did some years ago. Everybody remember that? They had this tracking app that would move the setter of a digital image around. So you were having a conversation on your computer and you moved off to one side, it would follow you in the zoomed in mode. Except it didn't work with certain melatonin ratios. And it was like, oh, your computers are racist. All right, so we're in the rumors, announcements, gossip, blather. Does anyone have any of the aforementioned gossip, blather, announcements? Yes, okay.
So I can actually talk about this publicly now because it's out in the news, but Rackspace, my employer, was recently purchased and taken off of the public trading window. So we're now privately owned. What this means for me and my future employment there, I don't know. We're probably not going to know until at least 3 to 6 months out because Apollo, the company who bought us, needs to do their due diligence and all that other stuff. So for now, it's business as usual, but just be aware that this could impact some of my ability to contribute in the future to SVFIG and or Kestrel or whatever else people are expecting from me in reasonable time frame.
All right, well, we'll relish your contribution this afternoon later. I recommend that if you want to provide the victims on the interweb context for your comments, introduce yourself first. That was Sam Falvo of, you'll notice his name is on the agenda for later today. There's something I wanted to know. Some people click on the agenda on Meetup and it doesn't do anything for you. And then you go to the agenda and click on Meetup and damn, that worked too. Okay, that's 2 in a row. So rather than press our luck, I think that the next thing we'll do is have a short intermission and bring on the next speaker.
Full screen.
Okay, I'll leave you to that. You know how to work this, so I will leave it to you. I'm going to go to the bathroom. Don't start until I get back.
Take the microphone.
I was going to, but that's what you got to do, though. It's a requirement.
The wireless does not let
Go that.
Oh, well, maybe
Well, we'll wait until Kevin comes back. We'll see. We'll time him.
So the festival was August the 6th and 7th. When did you go?
I went Saturday, and Kevin went both days. Yeah, more or less. You'll see what I saw, and you can make your own judgment. Wish I could have gone Sunday as well to hear some of the other speakers, but it's
The festival, I'll be Santa Cruz.
oh no, 1 year was actually at Moffett Field, before the Computer History Museum was moved over to its present location. And then I think it was at the Santa Clara Convention Center. Is that what you're talking about?
No, I thought it was out Santa Cruz.
Oh no, I don't. Oh, the only thing is down by Santa Cruz is the digital barn. Okay, Digibarn. Yeah.
Does the presenter actually work?
Yep.
All right, we've accomplished that.
Okay. Hello, everybody. I'm Dave Jaffe. Earlier this month, the Computer History Museum hosted the Vintage Computer Festival after several years of absence. So I was there. My camera was there. The camera took pictures, and here they are. So I have my own photos, and then there's some photos online from this place called Tech Republic. I think it's just about a dozen photos. And then if we have 10 minutes at the end, there's a video that I can show as well. So let's see. So here's the program guide that you got when you paid your money. And this has also been made into, the image has been made into a t-shirt that I'm wearing and Kevin is wearing. Very nice t-shirt, so commemorating the event. So here's the speaker schedule and exhibitors. I was just there on the Saturday, and I saw a couple of the speakers, but most of all, I like to look at the artifacts and the exhibits there. Lots of people showing off a variety of stuff, and I hope I can remember everything. And Kevin, you may be called upon to help. Yeah. So the first thing right indoors is Southwest Technical Products computer. Yeah, remember those? So it's a 68. It's a 6800 based system, homebrew system. Yeah, all of them were linear power supplies back then. There were no switching power supplies in '75. So here they had a whole booth on Southwest Technical Products. The the boards and other stuff. So it looks like they did a pretty good job here. Yeah, here's some of the boards. Timer, calculator, cassette interface, system board, control interface.
Someone's built himself.
I don't know, but back in at that time, a lot of the stuff was in kit form only. In fact, I remember I had an original Altair computer, and although the boards came bare, it was actually a little bit before the time where they had plated through holes. And so I remember a lot of my buddies who were building Altairs had problems because when they soldered it up, the solder didn't go through to the other side, making the contact that you needed from the top board to the bottom board. So that was an issue back then. This is a little Logic Microlab circuit board, maybe for teaching. This is this guy's analog computer integrator thing. I've seen this on several occasions where a lot of the stuff, even printing the output is done in a manual fashion. All motors and gears, and they can implement things like differentiators and integrators into this, and so there's one guy that does all the stuff.
This is all built with Meccano.
Yeah.
European equivalent, English equivalent of Gilbert Director set.
Right. Meccano is the mechanism and company that's used to build all the stuff. And down here you can see a motor that runs at least part of this stuff. So you can do analog computing stuff with this, basically. It's not a digital computer by any means. This is a digital computer. It looks like a digital made by Digital Equipment Corporation. This is a PDP-8M with 2 floppy disks on the bottom.
I worked on a PDP-8E when I was in graduate school. Wow.
I've got a photo later on of another PDP computer.
Oh, too cool.
Yeah, so this is a little, oh yeah, this is Space Wars. There's some controls down here, and it's playing a version of Space Wars on this monitor. Okay, this is a digital Data General 1 a laptop computer, and I actually had access to one of these. And what was really noticeable about it is that it was the first clamshell laptop computer. And these were very early days. In fact, it was so early that the contrast ratio of the screen was only like 2 to 1. Very difficult to see. So it had a floppy disk in it. And here's a little bit later version where they actually have a electroluminescent or plasma screen, with a lot more visibility. And in the middle is a ThinkJet printer, very compact, early printer at the time, using paper with holes at the sides. I think it worked pretty well. I never had one, but yeah. So that, yeah. ThinkJet.
Right. I'm just curious because.
No, it was a dot matrix, as I recall. Yeah. Yeah.
It had a cartridge with dry powder and like a piezo.
Yeah, I've had that nature. I was just wondering because I believe some of their early inkjet printers were used to like that.
Yeah, I had a.
These are all original.
Yeah.
This one wasn't. This had a little cartridge of powder, and the piezo would sort of bang the stuff out. You had to use special paper for it.
No, this wasn't special paper.
Now, the ones with the rivets were better in the sense that you didn't need the special inkjet paper.
Yeah. Okay, next is this Monopoly game-based computer. And you can see each of the players has this little data entry calculator type thing. And there's a big screen in the middle. And the buttons here allow you to throw the dice and buy or sell what you landed on here. So there were people playing this the entire time. That's sort of cute. IMSI. How many people had an IMSI computer?
Oh, yes, yes. Right at school.
Yeah.
8080.
Yep. So the 8080.
Processing line.
Yeah. So it was an Intel 8080 8-bit processor.
1 megahertz. Clock.
2 megahertz.
Was 2?
Yeah.
Ooh.
Yeah. So this used an S100 bus, and this came out after the Altair, and it was a little bit better in the fact that it uses these nice piano, these nice switches here, which you can arrange in hexadecimal like he has here. But it uses the same S100 boards as the Altair. This is Dwight Elvey's exhibit. And on the right is a Heathkit analog computer. And he opened the top of it. And in the front, there's about 8 tubes that are the amplifiers. And you wire it up in a way. And he was creating some images on the screen here. On the left-hand side is this Logic learning lab. And again, you connect things, and he had it producing a circle on the screen when it was working. So, yeah. So here's an image from the other side. So this you could actually buy this Heathkit analog computer. Okay.
One of the things he was putting up on the screen was a bouncing ball demo, and you could adjust the elasticity
Oh yeah, that's right.
of the ball and the gravity.
Yeah, so that was on this screen here. Yeah.
Might want to repeat that for the others.
Right. So what was being displayed is the computation of a ball bouncing on a surface, giving up energy on each bounce, and so it would show you the trajectory of the ball as it bounced. This is a PET computer, but it's a later PET because this one has a nice keyboard. The earlier ones, which I'll show you a picture of, had chiclet style keys. Yeah.
Oh, there's actually 2 styles. This one with the smaller screen actually came out with 80 column, whereas the ones that are larger screen.
Yeah, so there is apparently two different displays, one with 40 columns and the other with 80 columns. Yeah. To the right of the PET, this looks like a Commodore 64. And it had a little bit of color capability, and it ran BASIC. I never had one of those either, so can't comment too much. And this one says Irvine Computer Corporation. Is that right? I'm not familiar with this one, so not much I can say about it. So these are gaming computers.
This is a clone of the Texas Instruments.
Oh, yeah. Sam's saying that the one on the left is a clone of the which computer? The yeah, TI-99/4A computer, a clone. Yeah, it says based on the Texas Instrument home computer series. It was a commercial failure.
But something. But it's
Yeah.
Bill Cosby, it's still-
Right. So these are, again, knockoffs of other computers. This one looks like a Japanese knockoff of something running BASIC. And this one, I'm not sure what it is, but I took a picture of it anyway. This is one of my favorite computers. These are IBM 5120. This one, I saw this very early on, you know, probably in the early 70s. And what was neat about it is that it was integrated a monitor and the keyboard and all the electronics. And it was, you could lug it around. There were several versions of this. This is the version that had a built-in DC 300 tape for storage. And some of them had a switch over here, and it switched between BASIC and APL. And I thought that, excuse me. Okay. Right. So this one is also running an external monitor. And I recall a story of one bicyclist who had a backpack made to carry this to and from home so he can work at home with this computer before in the very early days. So it was all integrated. It looks like on the right there's another tape drive. Yeah, it says September 28, 1975. Yeah. So here's the tape, and these tapes were also used with microcomputers, you know, the home computers as well. It typically had an interface board, and then you can save and load programs from it, but it was very slow compared to a floppy disk, so it never gained any popularity. These kind of data cartridges were good for, you know, backing up stuff, you know, sort of offline. But they were pretty popular, but not very useful for a hobbyist, though.
If you had a 100 megabyte hard drive, backing it up with a quarter-inch cartridge is a lot easier than sticking 100 floppies in.
Right. Yep. So this is an Amiga OS 4.1 box. I think this is wasn't a Amiga box. Somebody just put the Amiga computer inside this chassis.
Actually, I can give more detail on
Okay.
that. This is actually not a classic computer in the sense that it's vintage, but it is kind of unique because it's one of the few surviving PowerPC motherboard designs.
You're right.
And Amiga, shortly after they left Commodore and Gateway, licensed an independent third party to produce new Amiga hardware.
Okay.
And they're actually still in production, but the company is losing money hand over fist doing this.
Yeah.
It's a labor of love,
Yeah.
basically.
So Sam says this has a motherboard in it that has a PowerPC. And do they supply the chassis as well as the motherboard? Okay. Okay. All right. Thanks, Sam.
That is a true hardware, though.
Yeah. So this is a real Amiga hardware, and as I recall, all the electronics are in here. Yeah.
Everything except the power supply.
Okay. Power supply is external. Monitor is obviously external. Looks like this is another Amiga. Am I right?
Yeah, this is an Amiga 2500.
Amiga 2500 with an external regular keyboard and an external monitor.
Yeah, and this is basically a slight enhancement over the Amiga 2000. I forget exactly what was the enhancement, but these machines, when they came out, were originally intended to run 18 TPS.
Oh,
With the addition of a CPU card.
okay. So Sam's saying with the addition of a CPU card, CPU card, these were supposed to run Unix, were designed to run Unix.
But that never came to be because shortly thereafter, the 3000 came out.
Okay.
And Unix ended up being running.
Okay. So Sam's saying that a follow-on model, the 3000, did run Unix, whereas this one never got to that point. Thank you. Some wire wrap boards. I'm not sure what exactly this was for. Here's an Amiga Developers Conference poster and some hardware at the top.
I can tell you what the wire wrap boards are too.
Okay, thank you.
The wire wrap boards are the prototypes used to design the Amiga's Agnes, Denise, and Paula chips.
Oh, okay.
The 3 custom chips.
Okay. So Sam says though those wire wrap boards were built to design the CPU chips that followed, right?
Yeah, video,
Audio, video, specialized chips. Okay. Yeah, Dell keyboard, we see that. I'm not sure what the rest of it is. Oh, I know what it is. So what it is this little, somebody made a PDP front panel that doesn't, you can control it as you can control the lights from an external computer. And so it's a very nice scale model of the front panel. And so maybe the idea is that you run an emulator on a more standard PC, and this provides the feel of what the front panel of the computer might look like when it's running. Yeah, so it's the PIDP-11 first prototype Medusa open source hardware planned to be offered as a kit in late 2016. Okay. So that was neat. So it's made to look like the front panel of a PDP-8/I replica. Easy to build, $145 as a kit. Oh, it uses a Raspberry Pi to run that front panel. Okay. Yes, this is the inside of an Altair 8800. I had one of these that I bought in the first wave of shipments, and so I remember this very well. So there was a front panel board that had all the lights and LED soldered onto it and the switches, and there was a CPU board that was just CPU and control ICs, and then there was a second board that I got that had 256 bytes of memory on it. And the whole thing came as a kit, and it cost like $397 at the time when an 8080 was going for about that same price in single quantity. So this was a deal. And these are S100 cards down here, and you can populate the chassis with up to 16 of those. The interesting thing about this design is that the power supply produced non-regulated power, and regulation for the power on board came from onboard regulators, which really dissipated a lot of heat. And that was fine, if you're computing in the winter and the room is cold, it would really be nice and toasty. But it's wasn't a good design, and a lot of people had to, upgrade their power supplies, and because you had to have a lot of boards, because the boards that you got for memory boards were typically at that time, 4K per board, and to have a really nice running system, you needed at least 16K of memory at minimum to run CPM. So, but this standard stuck around for a long time, and there's lots of other boards that have been made. So here's the front panel, and you can toggle in addresses and single step and enter data and look at data and stuff like that. So that's what all those front panel switches did. Later on, They had video display cards, modem cards, high density memory cards, and other CPU cards. But this was an original one because you can see right on top here is the location of the 8080 chip. Yeah. So this guy's got a whole box of S100 boards, and some of them say, you know, 386, Intel 386 computer and stuff like that. So there's a wide variety of boards and interfaces that you could buy and use. And so here's somebody's homebrew S100 box with a handle on the back. Yeah. Yeah. So this is a Diablo daisy wheel printer. I had one of these, and I got one refurbished, but it looked brand new for $2,200. And that was a deal at the time because the only other real printers out there were like teletypes. Yeah. Yeah. Yeah, I had one of those too. So the neat thing about this is it used a daisy wheel print wheel, which means you can have different fonts, but just by plugging in a new daisy wheel. And this is a beautifully built piece of machinery. It had a carriage that had whose back and forth motion was controlled by a servo motor, so you could move it 1/120th of an inch horizontally and 1/60th of an inch vertically. And I actually have seen programs where they plotted graphs using the period as the key to print a point. And so you could control that in software, and you can print a whole series of charts using that. It cost a lot extra to get a serial board for it. So what I did is I had a parallel port board in my computer, and I wrote a driver for the Diablo printer, and that worked out pretty well. So this is an ADM3 terminal, and it looks like it's connected to a North Star computer on the left here, which, well, the one on the left, it looks like it's just a single board computer, but I think the one on the right had its own floppy disks in it, and it was also an S100 system, as I recall. Yeah. This is an H19 terminal connected to an S100 computer. And I had a bunch of these terminals, and they also had a version called an H89, which had another board in it, which was a Z80 computer. And I got it to run CPM. The original version of CPM that came with it had a starting location different than the regular CPM, but I figured out how to resolve that problem. And I had, on my computer, I had a couple 5¼ inch floppy disks in that space there.
Were they hard sectored or soft sectored?
They were hard sectored, I think, 10 sectors, as I recall.
Well, a soft sector disk would have one hole.
Index hole.
Sector index.
Oh,
A
right.
hard sector disk would have as many holes as there were sectors.
Yeah. The old days, good old days. Yeah, that's a full-size 5¼ inch floppy disk and S100 boards. And so here's some North Star cards. And this thing was called the Monster 6502, single board computer that you can play with. I never saw these, but it looks like you can hook it up to a regular keyboard. But if you want to,
More inspiring than the Sim 1 and Kim 1.
yeah. But if you want a really big computer, you get this this learning lab. So it was a whole computer where you're able to see everything, and there's actually instructions and stuff like that over here that you can execute and see the results at the LEDs on the side. Yeah, so that was neat. So here's the instructions, stuff like that. So this is a large Cosmac ELF computer board, typical of the early days where you had a little keyboard, not much of a display, typically loaded programs from cassette tape. Yeah, those are neat. Jupiter Ace, yeah. So did this had a Z80 in it? Yeah, right. So this came a little bit after the Sinclair model. So this had a little bit nicer keyboard. Excuse me, you have one? Yeah, right. Oh, great. Yeah. Okay, so this is a Commodore 64, some kind of wire wrap card. I think these were Russian knockoffs of some other computers. This one and this one. And this one. Don't know a lot about them, or I forgot. AMI prototyping board. I don't have much details on this. AMI 16K RAM card. I think this is a cassette interface. This is a TRS-80 computer, color computer, yeah, with a mouse. So there were some of these mice that were really interesting that had photo detectors on it that were sensitive to red or blue, and so you actually had to run them across a mouse pad, a metal mouse pad, and it would count how many red or blue stripes it would run over to position the mouse cursor.
Is red in one direction, blue in the other?
Yeah. So you can really mess up your colleague by rotating his mouse pad 90 degrees. Color computer, Radio Shack color computer. So yeah, so this guy built this whole computer using TTL circuits, and it's like a full computer. It's on the internet. It's serving web pages, all TTL, even the CPU.
It's like MIPI, but a lot more evolved.
Yeah, yeah, yeah.
I think what he's using in there is, we call them the TPL.
Bit slice? No, this was
Yeah,
actually
it's bit
TTL.
slice. Yeah, that's what I'm trying to think, but it's
This computer was actually TTL.
TTL 181 chip, where you could actually build out, if I'm not mistaken. I'm just taking a guess.
Well, here's more information about it. Started in 2001.
74 series TTL chips, wire wrap.
Yeah.
Yeah, that's it. It's 74
Well, we like-
series.
Micro-coded.
What we like to call MSI, medium scale integration.
Yeah, because when I was at Calcom, they had built a graphics engine on boards that were like 18 inches by 18 inches. And they used the Schottky, that's what I remember, Schottky 181 TTL chips to build out the processor.
I think from what this says, it's all out of TTL.
Yeah.
And the guy did a great job. It's actually fairly compact for what it does. 32-bit address space, 8-bit data bus, 4 megahertz clock, hard drive interface. It has full TCP/IP stack.
Linux on that?
Yeah, Minix is a Uniclick OS. Yeah, so it's really very capable. Yeah.
200 chips with an average of like 4 or 5 gates on the chip. Pretty damn good.
Yeah. I'm not sure what this is. Looks like a homebrew wire wrap computer. Another one. Again, not sure what this was from. So this is a early IBM desktop computer running BASIC. Yeah.
If you look at the chart behind there, the point of this was the first IBM computer, no hard drive, just floppies. The first thing you can call an IBM PC. And he was running original Microsoft Adventure.
Oh, yeah, that's right.
Crystal Cave, Colossal Cave,
Yeah.
Adventure. You can see the chart on the back
Oh,
of that.
yeah,
So X, Y, Z, Z, Y, bang, and start.
yeah. Yeah, I had one of these as well. So the early,
Shortly after the Battle of Hastings in
yeah,
I want to say late 70s.
So this is before the IBM XP.
yes,
XP was the first one with a hard drive.
yeah, hard drive. This is before
Same
the,
processor, 8-bit bus, da, 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 da.
there was,
What I did with mine, I got the hard disk that was on one of the boards, you know, it was like a foot long.
yeah.
Plugged in hard card. Yeah. Believe it, actually worked.
Yeah.
Actually was able to load DOS on it and it booted from it.
Yeah, this one had a broken interrupt.
If you crack that thing open, is this a Model A or a Model B? Because Model A had 16K.
Yep.
Model B had 64. I had a Model B. I'm just going to keep that thing just to show
Yeah.
what the first person computer.
It didn't have 64. It had, it was missing the top 16.
Well,
48.
Is that
no, if you look at the chips inside, they were 64K.
It wasn't the first personal computer, it was the first IBM PC.
Yeah, that's what I meant.
Right.
first
And
PC?
this was the one, you know, that had the.
First IBM PC.
Remember the speed check they had? This one was considered one. And I think when they got like a 386, it was like, what, 2,000 tons faster?
Yeah.
This one was a tank.
Yeah. So actually, the first one didn't have a floppy. It actually had a cassette interface. And I had one of those. And the board spacing of the boards inside there were different. I had one with the, that I put a hard disk in it. And the first 5¼ inch hard disk I got had 13 megabytes on it. So those were the good old days. Not sure again what this is. So Multics inside. So this is obviously a computer that run Multics.
Why did they call it Unix? Because it's a castrated version of Multics. That's right. Yeah, that's it.
Yeah.
Multics is like Unix, only it's been castrated.
Oh, okay. It's an early version of Unix. Let's say. So, so this guy was really interesting. He collected TI calculators, HP, and so there's a bunch of them there. And I had one of them that was programmable. It actually had a metal magnetic strip, and you programmed it by basically giving the row and column of the button you wanted pushed at that point in the program. And so these magnetic strips went through a reader writer. And so you're able to save and load them off of there. So I remember a program that I wrote to test it. I'll tell you what the program is. It was a program to find two integers, A and B, such that when A and B were optimized to produce the closest value to an irrational number like pi. So you all know that 22/7 and 355 over 113 is pretty close to pi. But what's the next in that series? So, I mean, it's a pretty easy algorithm to do, and you can, and so, but to get that far, it would use up all the battery in the calculator. So he had to have it plugged in because it went for like about an hour to figure out what the next values were. So, but he had one of those as well. Not sure what this computer was. It's like, I don't know. Sorry. Whoa. Yeah. So these are just game computers. game over. I'm not sure what these were, to tell you the truth. So
Oh, God. These are-
yeah, so early disk cartridges, and this held maybe 5 megabytes or so on it, and removable. You had to put this in and have it spin up, and then you're able to access your data.
Yeah, that was the equivalent of the DEC RK05. That was the IBM version.
So there's a very nice display of these HP 85 computers, which were professional-based computers, very nice industrial design
This
with
was
floppy
the
disks.
First computer you could buy at a relatively reasonable price and hook up your voltmeter and your other HPIB at the time
HPIB interface, yeah.
and run a lab setup.
Yeah. So floppy disks on the left, solder off of it. I'm not sure the operating system, but it wasn't CPM. It was a
The HP85 ROM.
HP85 ROM. Here's the inside of it, very well built. In fact, there's Kevin had a link to a teardown of this. Very nice integrated CRT and printer and plotter and a tape drive.
GPIB tape drive.
Yeah. Yeah. Early Heathkit.
One thing before you go on.
Okay.
The guy had a spectrum analyzer.
Oh, all right.
With his, HP85 that he touted as software-defined radio, and he had it tuned to a radio station, zero bandwidth on the spectrum analyzer, and a little RF amplifier and a little speaker amplifier that lets us listen to the radio off of the spectrum analyzer.
Okay. So a little training kit from Heathkit. I'm not sure if that's a CPU there. Yeah, it must be some kind of CPU, maybe a 6800 or something. Not sure. Yeah, there's RAM and other things there. This is a MCS 85. So this is Intel's 8085 computer like starter kit. You had keys here. There's a little display here. There wasn't. They had a nice wire wrap area where you can put a UART and extra memory and stuff. And I remember having one of these things, and this was the first like embedded computer I had my version of Forth running on. So it was, yeah, pretty meaningful for me back then. They also made ones for 8086. This is a Data IO PROM programmer. I had one of these at the VA. And there's different modules that you can plug in here to program different devices. Enter the address and your data here. And very, very nice. And I can see this guy had the same problem. There was a little foam screen above the fan that apparently deteriorated over age, just like mine did. So, but very nice PROM programmer. This is an early pet. This is in the sales area. So this is the one that had the very low cost keyboard, but it had an integrated tape mechanism.
Suitable for use on the bridge of the enterprise.
Yeah, this is a Sinclair Z80. Apple 2GS, right?
So this is an interesting, it's the very last Apple II model to be manufactured.
With graphics, sound.
Yes. It had the 65816 processor, the 16-bit upgrade to the 6502. It ran at, we'll call it 2.5 megahertz. It's actually 2.3. The interesting thing about this computer is the efficiency of the CPU was such that it actually competed in application outperformed Apple Macintosh.
Oh.
And and so Apple killed the machine because of that.
Okay.
If I remember correctly, this is the one that sort of emulated the Apple II graphics somewhat in software or something. You could see the visual.
There's a chip on board on this that they used in the Mac LC plug-in card for Apple II compatibility. I forget the name of the chip, but it's the same chip, so it is actual hardware.
But it had like a blocky edge to the.
Oh yeah, like they maintain compatibility all the way back to the 1977 Apple II.
Yeah. Okay. Thanks for that additional information. It says Royal on it. I don't know anything about this other than it was for sale. Here's an Apple IIc for sale. Very nice industrial design. IBM XT with a monitor with green characters. This brought back a lot of memories for me because we had at the VA had a bunch of these Zilog computers. There are some of them that had internal floppy disk drives and others that were external. And actually got all these to run CPM as well. But as I recall, no, yeah. So this wasn't didn't have S100 cards in it. It was just single board, a set of single boards that ran this, and it worked pretty well. But I think the floppies might have been hard sectored floppies. I'm not quite sure now, but I used these for a long time. And if you wanted a floppy drive, here's a whole desktop worth of them. I'm not sure how much they were selling for, but lots of them around. Osborne computer. Yeah. Oh, K-Pro, sorry. K-Pro. Osborne had floppy disks on each side. Yeah, K-Pro.
Nice folded plastic. This is bent up sheet metal.
Yeah.
It's perfectly acceptable luggable.
Here's a bunch of Amigas. Amiga on the bottom. Yeah, and top for sale. Model 2000. S100 handbook for sale. This guy had this big 1130 system there that consisted of a terminal. Oh, I didn't know. I thought it was all part of the same thing.
One computer that was a hardware emulation, and one computer that was an actual genuine antique.
Yeah.
And both were running. This was the last computer built from discrete transistors, pretty much, sold in the mass market or the world of people that bought real computers. The transistors were bonded to ceramic substrates, so they had modules that were the effective equivalent of chips. This was an artifact of IBM saying, we don't know about this newfangled stuff. These chips, we're not sure. We're going to build something reliable and good and wonderful. And all the salesmen had trouble selling it because everybody wanted new integrated circuits.
Yeah. Okay. So there's actually people still selling S100 stuff, and I know that there's Altair replica machines that are kits. I recall one at the Maker Faire a few years ago that actually emulated Z80 in an ARM chip and could run CPM programs that way. Here's some of the images of the speaker. Oh yeah, this is, I'm skipping around a little bit apparently.
The IBM machine had a whole computer center.
Yeah, it's just a card reader. Yeah. Oh, and here's in the Computer History Museum the display of is this the 1401?
Yeah.
This is the 1401 computer.
It's gotten a lot snazzier. It looks like a real computer room. It's an exhibit now rather than just a bunch of old guys.
Yeah. So it's full. Yeah. So it's fully functioning, including the line printer over here. Yeah.
Interesting note about this one, it runs off of British Power. They had to have
Yeah,
a
right.
assembly.
Yeah, a 60 to 50 hertz converter. So there's a whole rack that accommodated that converter. This is this is a DigiBarn guy, who's the Bruce. Okay, I forgot his name. Bruce Dahmer, and he is the software archivist or whatever at the Computer History Museum. So he was talking about stuff at the DigiBarn, and this guy was he the guy that was talking about if there was how comparable CPM and DOS were?
Yeah, he did a forensic analysis
Right.
of DOS with CPM.
CPM.
You know, there was sort of stuff that he said you can watch the video online if you're interested in this topic. And that's the great thing. All of the speakers are, if they're not online already, they're going to be soon.
Okay, let's get back here. And here's a picture of Gary Kildall that was on the wall there, inventor of CPM. Yeah. And in the entryway, there's a big poster of Lee Felsenstein. He's one of the, what's the fellow of the Computer History Museum now. Yeah.
This is separate from Vintage Computer Festival. They had posters of all their inductees to their
Fellows, yeah.
Of the CHM program. He spoke at the closing talk, so I recommend his talk to you. If you want to go watch it online.
Is it online? Do you know for sure?
If it's not already, it will be soon. I
Okay.
don't know where it is right off the top of my head.
All right, I'll search for it.
Google is your friend.
And oh, here's a PDP 8. I forgot what model number this is. Just PDP 8. So I worked on this in school, and it had these boards called flip chips, which are about maybe 3 by 3 inches that had circuitry on them for, yeah, transistor circuitry for flip-flops and other stuff like that. And it had 4K of core memory. It was 4K by 12, I think it was. And I remember using this and a teletype and a paper tape reader to do all my first programming on a smaller computer.
Sort of the discrete equivalent of RTL logic.
Yeah. And I think that's it. So there's some more photos online, maybe about a dozen more. And there's a little video that maybe is more descriptive of some of the things in the exhibit area. So I'll post the links to those on the website because I think I've run over it. Yeah. Okay. Thank you. Thank you for your participation and your additional information.
Thank you for that trip down memory lane.
Yeah. Yeah. It was fun.
The other thing is that if you're interested in what happened to the original founder of the Vintage Computer Festival, Salamis Mal, his talk is on the program, will be or is already video available online.
Thank you. Yeah, you did.
You out?
No. Oh, yeah.
Thank you.
I just want to delete my. Oop.
I'll delete it.
Okay, thanks.
Are you gonna put those slides on the internet?
Yes.
Cool. Oh, that's my life right there.
Looks like the waterfall technique.
Strangely viscous.
Alrighty, so today's thing is going to be a hodgepodge of different stuff. To start, I figure I'll do the haikus because, haikus. You like haikus, great. There aren't a lot of them this time, so this won't take very long. That's actually from last time. So there's. Oh dear. We have a light cone here. It's delightful. Light cone 2, which seems to be pretty much the same. Mm-hmm. Bone projection. It would be. We could go back and do some. No. Oh. I think so some of my posters are upset because I, at some point, I think added a filter that excludes haikus that contain HTTP in the text of. Yes, well, I think they like to link to various places, strangely enough. So. Ooh. Ah, yes, they're still complaining about that. Not sure. Oh. I don't know. That's odd.
That's just. That's what that is.
Huh. This one seemed to have stages to it. I'm confused. Oh, there. Huh. Weird. A version of one we've seen before. But, Now in color.
So now that Hangout is going away, could Dennis have invited your machine to the Hangout?
We'll know next month how that will go. We could have done that this month as well, but yeah, probably ought to have. Yeah, next month.
We don't know whether it'll be really easy next month because we're here and not there. When are we? Wow, that's like totally awesome. How much code is that?
A lot. Doesn't fit it. Doesn't fit on the screen.
Dare I say dead trees? Would it be 2 pages?
Probably less than that.
Okay, well that's pretty cool.
Yeah. Yes, it is. Oh, this one sort of wobbles a little.
It's sparkly in the middle. Anybody remember the TV series Time Tunnel?
Yeah.
Looks like a manta ray flying down the time.
I'm assuming this one is small, as indeed it is. I don't know.
It's exponential decay across the x-axis. Stainless. Is that implying that there's somebody that's
I believe this guy, Stainless, is one that he's in the UK, and he contacted me once many years ago. Apparently, he actually used some of the haikus, or I guess he works in the games industry, and he was going to use some of the haikus in as sort of variable textures in the background of something. So. Yeah. Huh.
Hmm.
They aren't spitting you.
Hmm. Ooh, it's something. Polygonal comment. And then we're back again. That was, yeah, wrapped around. All right, so next on the agenda, I'm going to give a slightly extended version of something that I gave recently as a lightning talk. So I'm in a different context for lack of content. Adobe After Effects. I've had great fun with Adobe After Effects. It's a delightful program. I commend it to you, especially if you wish to do special effects in your presentation. It has a range of features. You can do keying, so you separate, foreground from background, possibly by color. You can do tracking, so you can have objects in a scene and you can follow them around, and you can. It's also very good at following the motion of the background. So if you have a wiggling camera and you want to get rid of that, you can use it for that purpose. It of course excels at compositing, and you can sort of put multiple layers of different things on top of each other, and you can layer different effects. And it has some facility for animation. It does a class of particle animations. It's not the most flexible particle animations I've seen, but it certainly can do a lot of the sort of common things you might want. It's a little bit bad at actually exporting. I think this is because Adobe would like to sell you a whole separate package to actually do the finishing touches and export your video to a final form. But it turns out that a lovely command line program called FFmpeg is capable of doing almost anything you might want to do. So if you're clever enough, you don't really need anything that.
Is this a program that they sell?
It is a program that they sell.
Is it in the cloud or is it
No, it is currently something that you run locally on your system. Yes, well, as I will mention, that such things will change in time. It is something that, mind you, you can buy as part of it. The model now, as I understand it, is you can either buy individual products, or you can buy a subscription in which you have the right to use the program for some span of time, and then you install some program that will monitor what you're doing and disable it when the time comes and all of that. Mm-hmm. They're collectively called the Creative Suite, I believe, is the.
I think they usually used to sell these individual packages,
Mm-hmm.
but now I think you cannot buy anymore.
Mm.
You can subscribe.
Mm-hmm.
Last I looked,
Mm-hmm.
you have to pay $600 a month. But with that, you can use all.
Yes, I don't know the current status. I happen to have a copy of what I'm guessing might be the last version that you could buy separately through work. But yeah, so.
But now I think it's CS6 or something, maybe it's 7 now.
Mm-hmm.
But the CS2 was released and still available free of charge. So the CS2 you can have Photoshop, you can have and back and all various things. So
Yeah, they're delightful programs, and my sense is that a lot of how they're architected actually goes back quite a ways. I mean, there's some of the plugins, even I think I'm running 6. They reference some. You can kind of see the vintage of how old the plugin is, and some of them seem to date back quite a ways, very possibly to the beginning. So they're delightful, especially with CS. Oops. I've lost the video feed here. Give me 1 second. There we go. They're great for producing presentation effects, and all the things throughout in this are from there. They can be, especially if you do a lot of particle effects and a lot of layers, they can be very CPU and actually GPU intensive. So if you have a system that supports something called CUDA, which is an API for giving programs access to your GPU, you can offload some of the filter operations onto the GPU, which can help. I have a desktop at work that I can do this on. It's kind of nice. It's a bit of a speed up, not as much as you might hope. And my hope is someday that it will be possible to run such a performance intensive application in the browser, but time will tell. That's me connecting this to my day job, I suppose. So you can do wonderful things like that. I gave this originally as a lightning talk. I'm giving the lackadaisical version of it, but lots of fun. So lightsabers. So the one fun thing that you can do with After Effects is lightsabers. But actually, let me talk about lightsabers for a minute, just for fun. So obviously, Star Wars 1977. Originally, the plan was, put some reflective material on a stick, and make sure it's pointed the right way at the camera, and this will look great. Of course, when Lucas actually filmed such a thing, it turned out it mattered a great deal which way you had the stick pointed, and very quickly it turned out this was not going to work. And so an animator by the name of Nelson Shin said, "Oh no, I can rotoscope that, no problem," and came up with the effect that we know and love. And he even sort of had in his head the notion of it sort of being a light bulb kind of a thing, and figured that the wiggle that you would get from rotoscoping, by the way, is this sort of tracing out on the actual film slides the individual frames, and the same effect was used all the way through to Return of the Jedi. Whereupon they introduced green lightsabers. Originally it was planned to be blue, but at the last minute the thought was, oh, there's lots of sky shots in this film. Let's have something that looks better on a blue sky. Jump ahead to the prequels, and a shockingly similar effect was used. The only difference is it was done digitally in the computer. You've got the dolls of various colors were used for the filming and whatnot. Something interesting happened actually with The Force Awakens, which is that devices like this became available, where you've got LEDs in them. And it turns out that this actually worked great in a number of ways, because they were able to use illuminated lightsabers on set. They still would do some post-processing afterwards, but as particularly when you see these lightsabers through cameras with the right lighting conditions, this is what you get with no editing. And so you actually get something fairly effective without doing a lot of work if you're so inclined. There was a blue one, a green one. Red is an interesting story, or at least the red one that I had my hands on, which is, you'll notice it doesn't quite look up to par. I'll talk about why that might be in a bit. There's at least a plausible theory that I have. So anyways, it's quite nice. The other nice thing about having them illuminated is that you get light on the various surfaces. And so surprisingly, in a lot of the, even in the prequels, there isn't actually a very good job done of other light coming from the lightsaber, even because that would have required quite a bit of effort to do well. So having on-set light apparently was quite an improvement. There are some interesting shots in Force Awakens that take advantage of this. So again, if you've got say a red lightsaber, you're going to want to do some post-processing on this to make the effect actually interesting and useful. So of course, if you're a Jedi, you need to know how to construct your own lightsaber, and you need to know what's inside. So I dissected one of these, or took it apart anyhow, and they're really quite simple. There's a plastic sheath over it, and then a second layer inside, and then just a strip of LEDs in parallel, hooked to a battery. There's a switch. Actually, part of what prompted me to take one apart is that this wire here broke free from a little shaking from whatnot. So there's a switch, and bless their hearts, they stuck a resistor on the end just for good measure. Yes.
The alternative is to have a little current diode in the base of the LED, which makes it a little more expensive.
Ah.
Not practical for this, because it's a diode. Otherwise, it will just suck as much current as you care to put in.
Aha.
Maybe blowing itself up in the process.
Yeah, it seems prudent to have the resistor. So let's talk about LEDs for a moment. So electroluminescence has been known for quite some time, but it was only starting in 1962 that you started to see visible spectrum LEDs. There were a lot of sort of early precursors, and they started to really get cheap in the 1970s. Apparently, the ones circa 1962, you'd pay on the order of like $500 an LED, so that, you know, not going to be used for much. The one interesting innovation is blue LEDs, fairly. Yeah, well, so the research was done in 1993, and these fun fellows actually had a great lot of fun together because they sort of concurrently developed aspects of this at the same time. Apparently there were lawsuits, all kinds of great fun, but they shared a Nobel Prize come 2014, so, you know, blue lightsabers, you know, can get you a Nobel Prize. Oh, yeah.
Why did they have to do that?
Yeah.
Look cool.
So in any event, if you take a look at the light that you get out of them, it actually offers an explanation for why that red lightsaber looks so poorly. So if you take the response curve of a typical CMOS camera, you know, you'll have a different bump for red, green, and blue. And if you superimpose the light that you get out of each of these different types, it turns out that while the green lightsaber fall in a region in which they have the opportunity to excite each of the colors, the red one, so they can saturate it in the middle when they're washed out, the red one only is able to excite the red and the green receptor, and as a consequence, does not do as effective a job of having a washed out center, or at least for the particular set of LEDs that I was using. My guess is that if someone was using this for filming, as demonstrated by that shot from Force Awakens, there are some other variants of LEDs that are actually a little more to the green side that you could probably get away with using. There are actually a number of orangish, amberish known LED substances. Yeah. Yep. But in any event, this After Effects is going to be useful if you actually want to fix any of this or to superimpose it where you don't have it. Because of course I should say that the other option is if you you know, and especially if you want to have your lightsaber retract, it can actually be inconvenient to have a permanent fixture of this sort. You have something like this where you know can extend and retract it and potentially just draw in the blade as you go. So we want to go from that to that. So how are we going to do that? So in After Effects, you can import various different formats. It's actually very good at importing a wide range of formats, practically anything I've been able to find. You pull it in, and then you glue them together into a composition. And there's the interface is kind of complicated, but you kind of grow accustomed to it. You can put, what's that? This is Adobe After Effects. So you have your various assets here, and then you drag them down into this area for to construct a composition. There's a timeline where you can assemble keyframes. And so then basically to rotoscope, for instance, you simply mark off a region. With a lightsaber, in most cases, you can get away with just 4 points if you're being lazy. You might want to do a little more if you want to be fancy. But if things are moving quickly, you know, it can go quickly. You have to put in keyframes. If you jump around a little, it'll do a pretty good job of interpolating. You can, by the way, there's a range of ways in which you can do this. You can alternatively try to do tracking. The lightsabers themselves are not great for tracking in isolations. The other option is that if you have them on top of a fairly uniform background, there are various filters you can do to just pull out the blade from the background, which can also be easier. But if you've got a sort of a range of different backgrounds, the manual rotoscoping ends up being sort of easy, and especially with 4 points, it's not a big deal to do it for a small amount of footage. So you mark off the points for each one, and then you can apply the sort of most common. There's a variety of different ideas on the interwebs as to what the optimum way to do this is, but the most common approaches seem to be basically that you take this rotoscope mask and then you apply a blur. In some cases, you apply a blur to multiple instances of it, and then you you superimpose that on your frame and then mess with the color balance in order to actually draw out color for places where it's washed out. And so then you get things like that. The other place that you can use the rotoscoping is in reverse. If you did have a blade like this and you wanted to remove it and have it retract, well, you can mark it, and if you've got some other piece of footage to map it to, you can pull things out of the scene, which can work as a poor man's way of retracting a blade. If you watch the clip that I've got here, you'll see that it's not a perfect thing. If you had camera tracking, as Lucas did even way back in '77, you could actually probably do a much better job, but there it is. So, and then of course you can add particle effects to do delightful things. So let me. No. So any questions on that portion of the presentation? He's just sort of sitting there. Yes, Kevin. Yes, indeed. Oh, yes. I will indeed. That's not the right link, by the way. Yeah. Ah! So, ooh. All right. Worth a second view. All righty. So I've got couple other little items. Oh, thank you. So let's see. Two fun things I'm pondering. So one of them is that I've been actually, you know, I'm not going to go to this one. Let me not do this one. So as I talked about last time, I've been playing a bit with Raspberry Pi, and I've been learning more about the GPU architecture there. And I thought I'd talk briefly about that. I'm still sort of working up the courage to maybe explore a fourth there. But basically, as I mentioned, the Raspberry Pi has a GPU called the Video Core 4, and it's actually shared across the family. And it's somewhat novel in the space of GPUs in that they have published the details of what you would need to program them. It's not a particularly advanced GPU by contemporary standards, but you can actually run code on it. It's an interesting architecture, and so I'm kind of scratching my head a little bit. Let me go back here. Yeah, let's see here. Zoom in on the. So it's got a fairly simple encoding for this is sort of all the different instruction formats. So it's very uniform instructions. They're big. They're I think they're what is it 64-bit instruction. And instruction. What's that?
Very long instruction.
Indeed. So there's basically there's sort of a register space of 64 registers, but only 32 of them are actually real data registers. The rest of them are control registers of various sorts. And actually even within the data registers, they're not all. I guess what is it? 16 of those are just general storage, and so they're actually kind of one hop removed. They're a little bit slower to load and store from. And then there's a few of them that are an actual accumulator and accumulators, and a few of them that have special behaviors in relation to the multipliers. And then but beyond that, it's sort of fairly simple risky thing. But here's the weird quirk: because this is a GPU, you've got what amounts to 16 of these. In practice, actually, what it is they're four cores, and then they're time multiplexed so that they're each sort of sharing. It's the same units sort of sharing the same space, but for all intents and purposes, it's 16 cores. But they collectively, I think it's groups of 4, share texture units as their access to main memory. And so the bit that's unusual with them is that because this is primarily meant to execute a shader, like the sort of thing that drives the haikus, they've been structured around the kinds of things you typically do in a shader. Now, these texture units, the way they work is that you typically pre-set up, you've got some image that you're going to apply, say, to the face of a triangle. And you've already pre-set up sort of the range in memory that you're going to look through. And so they're optimized to do a couple of loads to do samples that are then interpolated to provide you with points from the texture. But the thing is, this is a very high latency operation. And so what's quirky about it is that you enqueue a request for a load, and sometime later this becomes available. And you can actually fill up the queue with several of these going at a time. This same interface is used for general loads and stores to memory. And so not only do you have this for the texture operations, but just a plain load from main memory takes the same path. There's a local buffer that's nominally intended for a tiled chunk of image data. So you've got a write-only region. Actually, is it write-only? No, I think it's readable. It is a readable read-write region that's 64 by 64 that you can write to with relatively low latency. And the idea is that when you're rendering, you would be doing things a tile at a time and repeating operations just in that region. So you draw all the triangles into that region and clip them out, and then go on to the next tile and so on. The other interesting quirk is there is a facility for threading within each of these cores. There's two sets of registers that you can swap in and out. But this queue I mentioned for the loads and stores is shared by the two threads. So you can't just have arbitrary things going on, because they have to both be aware of what loads and stores are in flight when you toggle back and forth with them. So they're not completely independent threads. So there's basically 32 registers to work with, minus a few of them that are even within the general set that have some special purposes. Plenty of space in terms of the code size. Whoa, I need to not have that in this mode. Plenty of code space coming from main memory for the actual code of the shader, but the conundrum of how to cope with this unusual memory interface where you ask for something and then you can block and wait for a result, but to fully utilize the bandwidth of it, you ideally are enqueuing several requests before you actually expect the result to come back, which is a kind of a reflection of what modern sort of hardware is actually capable of doing. So I'm curious if anyone has any experience or ideas about what might be a good way to cope with this in a fourth.
That sounds like actually it's not fourth. The hardware was in real-time OS.
Mm-hmm.
Make a request, and basically, you wait. It's like an interrupt,
Mm-hmm.
right? Good example is modern Ethernet controllers. In the old days, they used to give an interrupt for every packet that came in.
Mm-hmm.
Now what they do is they say, oh, well, I'll give you an interrupt every 1,000 packets that come in.
Mm-hmm.
So you can get something like that, the equivalent here. You're going to need something kind of like an RTOS, which I'm going to talk about next.
Mm.
But yeah, you want to make sure that your thing is event-driven. So you can say, you make a request, but then you continue doing something else until you need to wait, which means we just like hand on like a mailbox or a queue, wait for those things to come in.
I mean, the thing that's, I mean, maybe I'm being overly aspirational here, but like when these things are used in sort of normal GPU operation, the planning is that you're supposed to, so they're emphasizing the idea that you've got lots of computational resources, and it's but high latency memory, and so the hope is that you're not actually waiting when it comes time to read. What you've done is you've managed to enqueue the things you're going to need ahead of time, so that by the time you need them, so there's a sort of juggling of balls thing here. That's
not real time.
So.
You really want to be able to have something that says where you actually wait. Now, suppose everything got done before you got to the place where you're going to wait. Well, you just come back and start processing. What this does is this thwarts any race conditions.
Hmm.
So you don't start processing until you actually have the data.
Mm-hmm.
So that'd be interesting. Now this is a video core.
Yeah, these are video cores.
It sounds like you would have to have a minimum of a tasking capability and inter-process communication.
So there is some limited, so in terms of communicating between the cores, there's some interesting primitives here.
Yes,
You can actually synchronize between them at various, you can have sort of a 16-way sync point where they all sort of rendezvous. The other goofy thing is that this, I mentioned there's this buffer, this 64 by 64 buffer of image data that you can store into. There's what they call what was the name? It's got a scoreboard. And basically there's a process where if you all try to initiate a request to it simultaneously, one of you will find out you've lost, and they're all, all but one of you will find out you've lost, and then you get to you have to retry. So ideally, again, you don't actually collide, but if you have to synchronize, you can work to do this. Yes, Kevin. This is pretty much it. So. Mm.
It's operating at SD-WAN plus.
Okay, all right. Well, there might be a way of.
If I may offer helpful advice going forward.
Yes.
I know it's too late now.
Yes.
People in the audience start blathering. Run over to them.
Ah, indeed.
Go get the door. Wrap it up.
Yep. So Paul, I'm going to close this down, but yeah, no, I'd be curious to hear your thoughts offline and.
This is the first time I've seen any technical details about
Yeah.
internals of GPU.
Now, I don't know how far people, so there's like one guy who's gotten some amount of stuff actually up and running for this, and the docs have been out, I guess, for a couple of years, but it's like, it's kind of interesting seeing the instruction set, and now I'm sitting here sort of like, what do I do with this? Like,
You know what this kind of reminds me? Signetics used to have a 2D accelerator that had its own instruction set that looked vaguely like this, although it was only 32 bits instead of 64.
Mm-hmm.
But it was surprisingly similar.
The break will be a little shorter than the original planned break. It went too long.
Right.
Because we were so excited about the things being presented. So expect that we will start up pretty soon.
So Dave.
John, don't forget to plug in your computer and try it out pretty soon now, right after you.
So you don't even have a Commodore 64?
Yeah, let's get
Commodore
your
64?
glasses.
No, I had
Really?
original LTIP
Yeah, no, I'm
that I used until I got a couple of DOS chains. But I sort of skipped over. There's a lot of things I skipped over.
60, the VIC 20 and 64 are like classic.
No, I was. So I didn't do any, the KIMs or the VIMs or the, those kinds of stuff.
Similar. It's the same problem.
Yeah.
Tons of local
You
combinations.
just gotta choose, what to spend your time.
Well, the thing is, because the Commodores, I skipped over the VIC 20. I heard that the 64 was in production, right? So, I mean, you get a lot more RAM,
Okay.
and
We change the subject.
it
List
had
of
better graphics.
Wi-Fi.
So I waited for that to come out. But in the meantime, like when I was in high school,
Okay, Starbucks save.
What?
And it doesn't connect.
um,
What's that mean? Does it mean?
I got to work on, because I worked in the computer lab, but I also worked in the office.
Sure, I can
And
see
because
how
of that
it's so-
association, I got to work on, all the Osborne and stuff like that, all the portables, with the little screens and everything.
So, yeah, this had a little one before, we're called Shauna. It was a really nice compact, built-in screen, and a floppy. Maybe it had, I think it had like the first three.
I had exactly the same experience today.
Yeah, I was doing all 5 and 4. You know, I was playing on the Tandies, when they first came out in the late 70s, because I was actually learning, I was going to Radio Shack, and they had before the color computer came out, remember they had the Tandy 1000s and stuff that had the big monitor, and then it had and if you're lucky, you had the dual floppy drives, right? And I was programming the internal basic and creating games while I was after school. I was, you know, the guy kept saying, you know, hey, get out of here. But, you know, I could show what the computer could do instead of just yapping about it, right? And one of the things that, you know, they don't talk about way back when is when they were doing the cassettes, both for Commodore and, you know, Handies and other machines, is that it was all audio squawking input.
Oh, yeah.
You know? And,
yeah, so, the first, first researchers on audio, I found one of these surplus modem handsets.
yeah.
And I converted it. I converted the frequencies, but I had it converted on that first modem frequencies, but they were like reversed. Like this, actually, where modems come out on the cassette tapes.
I don't know. I mean, I just it's timing. It's timing. So this is not as fast. It'll do. Yeah.
One of my colleagues did the original.
Back in the 4000 series.
I'm not this impressed with the size of the cover. It's not just one cover.
Impressive.
This is why.
You guys went hard
I'm assuming maybe what it is that you had actually.
I did most of my stuff.
Get my way, and with battery power.
Okay, well, you can the charger up with you.
Yeah, when I first came out here.
Okay, you don't have enough battery power to get to the front of the room. I'm scared. I could have brought you an extension cord.
A number of years.
So, when is it alleged that you were going to start originally?
Yeah.
Okay, you still have a few minutes before people are expecting you to start, so
I still
relax.
got a spare keyboard from my Commodore. I've got both the color screen and also the green screen. And I have a slot adapter which converts 40 to 80 column.
Oh, right, yeah, 80 pound power.
And I also have an EEPROM burner, as well as the blanker where you can actually write it to different banks.
Yeah, there was a, oh, it's called Lightsaber board. And yeah, you can program 27 weights.
Yeah, I still have all the EEPROMs.
Yeah,
It seems so terribly wasteful to have something so.
Yeah, that was pretty cool.
Yeah, I did a lot of stuff. Oh yeah, but the CPM and getting software on other guys' computers. You know, who had different.
Which is, so those, I don't see any of them. You can tell that I actually track the blade, I was having to super record behind you. There was a little bit more.
Well, it was more of a system process.
Same.
Software.
Remember turning single-sided into double-sided?
No,
You're doing hole punching? Use the
No,
hole
no.
puncher to flip the other side?
Oh, yeah, I think I knew how to do that. But most of
You have to be careful, otherwise you clip at the edge of the floppy.
Yeah.
That was always,
Yeah.
oh, Yeah, when you screw up, you do it good, you know?
I still got my Alta around and floppy disks, and I got another STD bus CPM system. I never did get to the process of transferring files from DOS to CPM or CPM to DOS. It would be nice to get some of those programs, and even the fourth.
Okay, I'm still having problems, so please.
We're in Philadelphia, and they said, we're going to have autonomous Uber cars. For now, they're going to be safety drivers, engineers sitting in the front with the steering wheel ready to hand, and hopefully they'll pay attention and not watch Harry Potter videos. But it should be interesting. Think of it as evolution in action, as one famous science fiction author put into one of his books. That phrase means we're going to do something really stupid and kill ourselves and thus eliminate ourselves from the gene pool. That's what that phrase means. So what does Tesla do when somebody crashes one of their almost autonomous Teslas? Do they take them off the market? Do they turn off that feature? No, they just say, oh, we'll put more LiDAR sensors on there and it'll all be fine. What's wrong with this reasoning?
Sounds like Microsoft.
Well, I don't know. Microsoft,
wait long enough, maybe you'll.
Microsoft, at least they used to say, don't use this for any medical or
Right.
online thing.
Something where someone's life depends on it. What they actually say is you cannot unless you get written permission. And it's going to be something worse than death by pink belly.
I remember one of our esteemed fourth colleagues went to a class on certifying software for medical applications, and at the end of it says, now ours is based on Windows. Is that going to be a problem getting it certified? And everybody laughed, except the idiots that were asking the question. So you got yourself sorted out now?
Hold on.
Some semblance of sorted out?
Let me see if it comes up. And
Certainly hope so. When you're ready to start, make sure you introduce yourself, because
I will.
on the other end of the pipe, they have no idea who the hell you are.
Okay. I'm not going to start right now. You can continue blathering, please. Yeah. Oh, yeah.
No. Just goes to show.
Okay, and let me. And it's
Capital A.
August 27th.
August dash 27th. I was going to say, but I had my hyphen removed.
Thanks for music with the sponsored guest.
Right. Okay. That's what I wanted to do. And let's see. Come on. Yes. Yes. Okay. You guys ready? Oh, looks like I got two jalokes back there that are doing face feeding. Okay. Hello. My name is John Harbold. My goal in life is to be able to integrate Forth with a real-time operating system. Our good esteemed colleague Kevin here put a notice out on the mailing list saying, oh, guess what? This company, Micrium, will give you the source to their operating system. It was something called Micrium for Makers. And I thought, cool. I thought that really looked nice. And it's for a whole bunch of architectures, ARM, you know, MIPS, whatever. Looked good, except for one thing. I wanted to initially get this stuff to run, especially in this case, Forth to run it under an RTOS under Linux. I mean, to have it run, no, not run under Linux, but to run it virtual on an i386 architecture. Unfortunately, these guys don't have it. But like I said, I have the source, and when I get time, I will write an i386 version of this. All right. So what I did was I got on the net, and I said, well, there's got to be another operating system I can use, and lo and behold, there is. And this is it right here, RTEMS. And RTEMS initially was called, the acronym RTEMS meant Real-Time Executive for Missile Systems. So if you guys wanted to build your own ICBMs, this is the software you want to use. Then it got changed. Then it got changed to mean real-time executive for military systems. So if you wanted to have your own combat robot, this is the RTOS you want to use. Well, eventually it got changed to this guy right here, real-time executive for multiprocessor systems like SMP. And one of the things that I noticed, you can see down here, here are the architectures. You have ARM, PowerPC, Intel, Blackfin, MIPS, Microblaze, and a whole ton more. The important one is this guy. Excuse me, was there a question? Yes, that would be nice.
This button right here. Don't put it in your eyes or my eyes.
Okay. So here we go. Right here. These are the guys. So what I did was I said, oh, great. I'll download this. And after several abortive attempts, I was able to build a version that ran on Intel, and I was able to use QEMU to run it virtually. And let me give you a little example there. Okay, come on. All right. This is a program called File.io, and let me run it for you virtually. Here it goes. So when I hit the space bar, I get this prompt. And one of the things that's, if I can remember offhand, it's got this thing called part table initialization. That's partition table initialize. Do that. Then mount all disks, this F guy. Then I'm going to try to see if I can remember. I'm going to list a file. That's the ISSEU.
And no, it bit the big one. Well, who cares? Well, I'm going to start the shell here. As you can see, where is it? There, right there. Use this guy here, start the shell. I'm going to log in as root. Doesn't have a password. And these are the help. These are, see these? These are all the commands you have running. This, now mind you, I want you to understand, this is not running under Linux. This is running under RTEMS. And this shell right here, you can see you have all these commands you can run along with fdisk right here, and my favorite, cup size right there. You have all these guys. So actually we have here, let's see, let me see if I can mount. Oh crap, I'll forget about it. Anyway, here's an example. I'm running this just like a shell. What this now allows me to do is I can write my own G4 shell and be able to have it run G4 as a program. Now, the problem is I have to build it, and I ended up fat fingering my code, actually not the code, but the build system. In particular, I stepped on string.h in my stupidity haste. So anyway, what's nice about this is I can now have a shell, which means I can operate just as though I were on Linux, which means I can probably use, if I wanted to, I could probably bring in an editor, you know, a small editor, so I could write a bunch of Forth scripts, or I could actually use the original Forth editor where I'm using screens. I can do that too. Now, with any luck, if I can get back on track, hopefully next in September, will be able to demonstrate that G4 will run under RTEMS. My next goal then is to be able to include the tasking aspects of RTEMS. Now let me do that. Let me show you. Okay, RTEMS, okay. Wait a minute. This is not right. Hold on, hold on. Oh, lovely. Oh, here we go. These show all the aspects of RTEMS. You know, there's, like I said, initialization manager. We have a task manager, which allows you to write tasks. We have an interrupt manager, which lets you write interrupts to attach to pieces of hardware that you have. There's also a clock, timer, where you can have semaphores, message manager, which, like I was talking with Sam there about when you have a task and what it's doing is waiting for work. You can have a mailbox or a queue or an event so that it's just waiting for work to do. So that if you have an interrupt that says gets data, you can create a data block, send it to a particular task, and the task can process it. There's also, you can see, just like in regular Linux. You have a signal manager. Oh, this partition manager. You all are familiar with malloc. Okay. Well, with this partition manager, you can set up memory pools of buffers of a particular size. So you can just say, go to a particular pool and say, give me a buffer, and let me do the processing. And when you're done, you free it up. And also, oh, look at this. This is something I didn't know about. Dual port memory. You can have that guy. And then, oh, scheduling. Okay, that's part of tasking. And then there's a lot of other stuff. Oh, stack bounds checking. Because a task operates autonomously, it has to have an area for a stack area. And this is also true with Gforth. Now remember, Gforth, you know, I mean, yeah, the task is going to have its own memory, but on top of that, you're going to need room for a data stack, a return stack, floating point, locals, whatever. That is something that's really nice. So my next goal is, after I get Gforth executing under RTEMS, is to be able to give the operating system API, so that I can write I can write tasks under Gforth and have those things executed. It's just like I did before. Several months ago, I wrote. I was able to completely port pthreads for Gforth, and then be able to test all the pthread executables, and they all work. And if I have any kind of luck, I should be able to get that same stuff will operate also under RTEMS. Okay, then after I get that, then I'm going to do something rather ambitious. Is I'm going to get something maybe like a Raspberry Pi running under that. And the nice thing about it is, as you all know, Forth is interactive. So you'll be able to interact with your tasks. I don't know if anyone has ever modified, I believe it's the inner interpreter, so that you can set breakpoints within a fourth word. So you can single step, you know, step over, step in, things like that. Look at the data stack, but have it set up so that you'll get a breakpoint, not only for a fourth word, but also for a particular fourth task. That's another one of my goals. Also, one of the things that I ultimately want to do is be able to, I'm sorry, I forgot one other thing. RTEMS supports USB, both device and host. So this Raspberry Pi that I would develop, I would actually turn it into a USB hub, so that I could, if I wanted to, I could plug it into a PC. And one of the things you can do is I could connect the serial port that Gforth would use and have it go out the host interface. So I could be on my development system and just hook up through a serial port to the Raspberry Pi as it's running. I'm really excited about that, because one of the things that USB does is you can have multiple devices on one cable, as you probably figured that out. And also another nice thing is I'd like to be able to get this so that it supports USB 3.1. And USB 3.1 transfer clock rate is 10 gigabits per second. So I'd like to be able to use isochronous transfers for whatever application I wanted to do. You know, even make my own. Well, yeah, but hardware is constantly evolving, and so probably by the time I'm ready to do that, we can get something like that that has USB 3.1. So, like I said, it took it took a lot of effort for me to get RTEMS running on my laptop. But now that I have it running virtual, now I want to get G4 to run under that, and then from there, you know, I can do basically anything I want. So, any questions? Yeah.
I know that in the past you were working with ECOS. Why did you switch from
Okay. One of the things ECOS doesn't support is dynamic linking. RTEMS does. That's what's important. In fact, when I did the P threads that ran under Linux, supports dynamic linking. And dynamic linking is like the difference between linking and dynamic linking is like early binding. Dynamic linking is late binding. So while a program is running, I can say, oh, well, I want to bring in another library to use. And that means that's any library. And if anybody knows how big the C runtime library is for Linux, it's enormous. So that's a lot of software that you can use that you don't have to write. So, and also the other thing that I found out about G4, it has its own Windows thing. It's called Minos, something like that. Oh, also, I'm sorry, that's another thing I read on one of the mailing lists. RTEMS has something called micro windows. So you could have your own windowing system running under RTEMS. Because, oh, let me show you what I'm talking about here. You'll notice that when we ran this executable, this window popped up. Now, if I change the size of the window, the only usable screen that I have is see what I mean? It's only, you know, the normal, I don't know, 80 by, what, 24 lines? Yeah, this would be nice if I could have a window that I could expand out to whatever I need.
Now that you're looking for all these little RTOS, you know, there's one that's been out there for a long time. It's SourceBoard. It's the free RTOS.
Free RTOS has another one, yes. Yeah, I could do that too if I wanted. But I don't know if I offhand, I don't remember if there's an Intel version that they have that will run virtual. Oh, again, that's what I'm saying. I just picked RTEMS just to do the thing. I could also use, like you say, free RTOS. If I had the money, I could actually use, say, VxWorks. You know, I can use whatever real-time operating system. Now, you kind of wonder, why would you want to do that when Forth already has a multitasker? The difference is the multitasker is a cooperative thing, and it's not real-time. So you want to do is, the reason I want to use a real-time OS is it's preemptive. And I can hook into whatever interrupt or device that I want to use. So I can, and also when you do real-time programming, you want to make your system event-driven. Don't poll. Polling is bad. Polling is slow. That's why we have interrupts. That makes things a whole lot simpler, and you can do whatever kind of throughput you want. So in the future, if I get to the point where I have my own USB hub that's running whatever RTOS that I have, one of the things I could, you know, normally you know what a hub does is you can plug into a computer and then you can plug whatever USB devices and the computer will then can access it. Well, with this RTEMS, I can say, oh, but if you plug in a particular type of device, the host computer isn't going to find out about it. You can then play with it in your RTOS, in whatever RTOS you have. I kind of learned this thing at another job, but I don't want to say too much because I don't want to get a financial pink belly from them. All right, so yeah. Oh, this is free. Yes, it is. That's the whole idea. You want to, the idea of this being free. Yes.
So, unless you want to sell it, make a bunch of money, make it into a product, then it's not free.
Right. And if heaven forbid, somebody says, yeah, I'd like to do that, well, then I would say, okay, let's get a well-supported real-time OS, and has gone through that's been thoroughly tested, of liability kind of stuff. Because one of the things I'd like to be able to do, one of the things I like about Forth is, if you write all this real-time code in C, there are such things as C decompilers. Right, which means you can give a stream of assembly language, and that code can be turned back into C, if you can believe that. And as you know, Forth is just a bunch of, it'd be like pointer chasing. Also, another thing I'd like to be able to do is, I don't know if anybody here has ever done it, is you've heard of making headless Forth, where you clip off the name field and all you have is just the pointers. That's all it is. So that kind of obfuscates your code, and I can tell you, pointer chasing, it can be rather tedious. So if someone gets a hold of your binary, all they're going to see is a bunch of pointers to code, and it can drive someone nuts if they wanted to try to reverse engineer this. So, yes. Oh, yes. Oh, yes. I'm glad you brought that up. Okay. Right here. This thing called RTEMS Center is, they're using RTEMS. I mean, the ESA, you know what the ESA is? European Space Agency? They're using RTEMS. So this is a well-used system. Yes. So you can see, yes, there are all sorts of tools and whatnot. I'm just saying, okay, instead of writing your code in C, write it in a man's language. Write it in Forth. Because I figure that everybody in this room and out there in the audience, they have sufficient brass in their programming testicles to be able to write code in Forth that works in a more cogent manner. Excuse my babbling. Anyway, so any other questions? I think I've gone over. Oh yeah, there's one. Yeah, that's the other thing. Oh, here's the other thing. You could, you can write. When I get a hub, an actual hub, I can actually write a GUI that polls, that not polls, but accesses the various aspects of, of GForth. So I can have a Windows version up there. And like I said, also changing the inner interpreter so I can set breakpoints and be able to step through code. That would be a really nice thing. Be able to have a window that shows what the stack is for a particular task. That would really be very, very helpful. Okay? All right. Thank you. Okay. Who's next? Santa?
Yeah.
Oh, Santa.
Santa Falvo. Santa Claus? There you go, Santa Claus.
There you go. You know where to stick this.
Take it, stick it.
Okay, let me grab my stuff. Before I do that,
It's okay. I need to find the HDMI cable.
oh,
Oh, you have HDMI?
okay. There you go. There you go. All right, now, because it's dark, I can't really see, so I don't want to drag anything because I don't have my battery is
Okay, so
really
that's
weak.
VGA. I'm now looking for HDMI.
Oh, there.
Ah, good. No, well, we'll see. If this doesn't work, then maybe, but we'll see.
Here.
If I'm lucky, this will work.
Oh, Sam,
Yes.
our task works on risk. I think that they're talking about using open risk.
So OpenRISC is one type of free CPU, but if it works on MIPS, it'll definitely work on RISC-V.
Cool.
They're almost assembly language compatible. Hello, folks. My name is Sam Falvo. I have been working on a home computer project named Kestrel 3. The third iteration of this design is intended to use the RISC-V CPU architecture, or RISC-V instruction set, I should say, which I've been attempting to implement myself in Verilog, to which has heretofore failed miserably. And the reason that it fails miserably is because there's at least 2 orders of magnitude complexity difference between even the simplest RISC implementation and a minimal instruction set computer. And I think nothing demonstrates this more than comparing the lines of code of one of my MISC architecture CPU designs to, which typically comes in between 300 and 600 lines of code, to just the instruction fetch logic for my homebrew RISC-V implementations, which after you get done fetching the instruction and coming up with a basic decoder for all the instructions, you're already looking at about 1,200 lines of code. And this is not covering the register file, this is not covering the actual execution engine, and it's not covering memory I/O either. Start out with asking the question, can we simplify this design somehow? So I've attempted to make my RISC-V processor in raw Verilog by hand, about a total of 3 times now. And all 3 times I just gave up in frustration because I very quickly lost intellectual control over the design. So then it occurred to me, well, if Intel can take complex instructions, translate them into RISC instructions, and then execute them in line, then why can't I take RISC instructions and convert them into MISC instructions and execute them in line in the same way? I already know how to make a MISC processor, so this should be relatively straightforward. And after some researching the matter, the obvious answer is, of course, yes. We already know of one, admittedly, it's interpreting another stack CPU, but we already know of one basic proof of concept, the BITSI processor that John Reibel has done with the green arrays chips. So we know that it can be done, but the question that I wanted to answer is, can it be done fast enough? It's one thing to emulate another MISC architecture such as BITSI, but attempting to emulate something as complex as the RISC-V instruction set, which in the global scheme of things is actually pretty simple, but there's no arguing that it is more sophisticated than your typical MISC architecture. The question is, can I do this fast enough to satisfy my requirements for user, for a computer that's actually usable by the end user? And the answer is, of course, yes. Long and short of it is, you have to be very careful about your instruction set design and things like that. So I started off the presentation a little bit with the background, so I'll just move on from here. So basically, when I worked on this, I tried, like I mentioned, 3 times before to implement this. The first attempt was a genuine 5-stage pipeline, exactly like what you would find in Hennessy and God, I can't remember his name now. There's 2 people who wrote the Patterson. Thank you. Hennessy and Patterson wrote a book on CPU architecture, which specifically outlines how to implement RISC architectures, and that's the approach that I initially took. It seemed to take the least amount of logic. I would argue that it is, in fact, a simple design as RISC engines go, but there are so many control signals that go between different pipeline stages that it was really difficult to keep them in my head. And since I'm the only person working on this, that's, of course, of vital importance, because basically I got to the point of implementing support for an add instruction and an instruction fetch instruction. And then after that, it was like, okay, where do I go from here? You know, what's the next steps? And every time that I would try to support this with unit tests or bench tests, as they're called with Verilog, there would be this combination or combinatorial explosion of all these different edge cases that I would have to look at. And so that was untenable. I could not really work with that. The next steps, the next 2 times, I attempted to use hardware, hardware microsequencing. And this comes in 2 forms. You have what I call the 6502 model, where you have your instruction decode implemented as a collection of and/or invert logic, hence the PLA circuitry. And the other approach is what I like to call the Z80 model, which is using horizontal or vertical microcode of some type. And so I tried both ways, and again, I lost intellectual control. At about the same place, actually. I got instruction fetch working, I got addition more or less working, I even got illegal instruction detection kind of working a little bit. But then after that, it was like, again, okay, where do I go? What do I do? How do I do it? And how do I express this in a form that I can confident that the design is going to work? So those cases, like I said, I just lost the mental capacity to put it all together in my head. So then this is where I came up with the idea of the stack ops decode concept, where we translate RISC-V, a single RISC-V instruction, into an equivalent sequence of MISC instructions that the MISC core will actually execute. So I did actually come up with a very crude prototype. And in doing so, I ended up creating a new MISC core, the S64X7. This is, in a sense, the logical successor to the S16X4 that powers the Kestrel 2. And after several months of trying to get the Polaris RISC-V CPU architecture off the ground, I implemented the S64X7 in frustration in 3 days. Admittedly, I don't have interrupt support or CSR support, but those are relatively easy to add. I know how to get there. and writing the bench test for those is fairly trivial. Now, in this case, the initial design is not intended to be particularly fast. It, just like the S16X4, it executes exactly one instruction per clock cycle. It turns out that the average number of clock cycles needed to implement some of the more complex instructions, in this case here, I've got, let's see here, 2, 4, 6, 8, 10, 12. So you would expect something like this to, actually 13, because I forgot to terminate it with the instruction to fetch the next RISC-V instruction. So basically, roughly 13 cycles. So one of the most complex instructions in the RISC-V repertoire would basically execute in the same amount of time as your typical TMS 9900 instruction. But this is basically what, sorry, I scrolled too quickly. This is essentially what we're looking at in terms of translation. So here we have an addition instruction where we're adding a constant to a source register and depositing it in the destination. And it looks like just about any other fourth code to do the same thing, right? So you push the source register address onto the stack, you set the A register, and then you read from the register file as a separate instruction. Interestingly enough, if you look over here, we write directly to the register file using a single operation instead of two operations. And the reason has to do with how the block memory works in the ICE40 series of FPGAs. So this is all based around how the ICE40 works. It has, unfortunately, for me, a synchronous read operation, which requires one clock cycle to set up the address. And then in a subsequent cycle, that data becomes available where this opcode picks up that data. Whereas synchronous writes, with synchronous writes, you present the data and the address at the same time, and then the next clock cycle, it latches that data into block RAM. So there's a certain asymmetry in access patterns. So this is a jump and link. This is the instruction that you use to implement both unconditional jumps and unconditional subroutine calls. And it works just like you would expect. We fetch the current program counter, we stuff it away in the destination register. We then add, this should be instruction address, not PC, but close enough. We take the jump and links instruction address, and then we add the offset to it. We set the program counter, and then we fetch the next instruction. This is an instruction to read and set a certain set of bits without affecting other bits in a CSR, or CPU-specific register, kind of like Intel's MSRs. That takes, like I said, about 13 cycles if we were to implement that naively. This is the pipeline layout. It's not really a pipeline per se, because ultimately everything, as you can see here by all the arrows, I wish I could reduce this font size easily without having to go to preferences. But long and short of it is the MISC core, nothing works. You have to go through preferences to change it, and it's kind of a, yeah. You would think that they would add that. So basically you have the MISC core, which is really the brains of the operation. And as you can tell by all four of these arrows, it is the one that's ultimately in charge of everything. So it instructs, by way of that next instruction, it instructs the instruction fetch unit to present an address to memory, which you then grab. It passes that to the stack op decoder. So here we're taking in a 32-bit word that represents the instruction, and we're putting out 64 to 128 bits, roughly within that region. That contains all the MISC instructions and all the operand information that replicates the desired behavior of that RISC-V instruction. That information then is fed into the MISC core as part of that next instruction. And then we start executing from the very beginning of that instruction word. And from there, we have access to the register file or to data IO as well. So architecturally, this is simple. Doesn't look like it compared to a regular 5-stage pipeline. This looks like there's a lot more complexity involved, but it's actually architecturally quite simple. Most of this is actually just combinatorial logic, very, very small amount of sequential logic involved. So it is definitely possible to do this architecturally. We have proofs of concept in the green arrays chips with the BITSy processor. And it's and as long as you replace the software emulation of the external processor with a hardware implementation, we can make it basically decode any instruction set we want. You want an x86 processor, all those blocks stay the same except for the stack ops decoder. And as I mentioned, this is roughly as performant as a TMS 9900. So you're looking at an average of 12 cycles, between 8 and 12 cycles to execute an instruction. So it's actually just a smidge faster than your average TMS 9900, but still in the ballpark. However, what I'm looking at, in order for the Kestrel 3 to be competitive with the Commodore 64 in terms of human interaction at the keyboard, I need something that's about 4 times faster than this. And that really puts a strain on the MISC architecture as it's naively implemented.
Are you basing that on sort of impressions of systems implemented in the 99?
Oh no, the question was if I was basing this on impressions of systems built around the 9900. No, you can actually get data sheets on the 9900, and most instructions on the 9900 take 12 cycles.
No, I just mean in terms of your performance rate. Like they're objective.
Oh, how did I figure out that I needed 4 clocks per instruction? So basically, it involves screen update response times. The Commodore 64 has a bitmap mode that is 320 pixels across by 200 pixels, so about 8 kilobytes of memory. If I were to write a very simple, naive loop that just clears the screen and nothing more, right? It's just this drop-dead simple loop. It takes about roughly half a second to a second to clear. This is at assuming a 1 megahertz 6502, which translates to about 0.5 MIPS performance. If I take that code and translate it to RISC-V, not assuming a wider word width or anything, just literally just storing bytes, not half words, words, or D words, I would need I could achieve a similar amount of performance as long as I have a similar size bitmap that I cleared. But since I have a bitmap that's about 5 times the size in terms of memory space, my base performance to get that same visual feedback now comes to about 5 MIPS. The VGA clock runs at 25 megahertz. So if I divide that by 4, the closest thing I get to is about 6.25 MIPS. So as long as I stay somewhere between 5 and 6 MIPS, then I will have a comparable degree of performance. So there's a couple of speed up techniques here. If we stick with Chuck Moore's definitions of MISC instructions, things can work, but it will definitely take a lot longer than it needs to. We can actually simplify the architecture if we add specialized instructions specifically and purpose-built for this task. So we've already seen a few. We have RA to set the register address and RF fetch and RF store to read and write to the register file. There are others as well. I won't stick to that too much, but this is this has long been a staple of stack CPU design techniques. In fact, I've been involved with numerous debates on the Silicon Valley FIG mailing list discussing whether or not this is a good approach to take for certain classes of applications. In this particular case, it is definitely a good thing to do. But there are limitations, right? So as you add more specialized instructions, you obviously need more bits in the opcode, which means that the path from the decoder to your MISC core gets wider. And that uses up even more FPGA resources. So eventually, you could very well run out of opcode space if you go hog wild with this technique. Thankfully, there's another approach called macro op fusion. Now, this is, I would argue, the most powerful weapon that a stacked CPU has against superscalar architectures. Because we hear it all the time, you can't use superscalar techniques in stacked CPUs. You just can't. It's too sequential. But it turns out that if you use macro op fusion, you can actually reclaim a decent amount of performance that you would otherwise get with a more complex superscalar architecture. You won't exactly match it, but you'll come close enough. So again, it's not superscalar execution. We only have one execution engine. However, it is with a sufficiently complex instruction set decoding, a random logic as it's called, you can come very close. So if you want to compare a four-way superscalar against a circuit that decodes up to 4 instructions at a time, then the macro op fusion will allow you to approximate the superscalar's performance. And this is particularly relevant for stacked CPUs because often you'll find things like a good example is adding a literal to an address and then fetching. Because of the stack order requirements, you always see the same pattern for all the time. So if your instruction decoder recognizes this as a single instruction instead of as 3 separate instructions, you multiply the performance of that indexing operation by a factor of 3. So that's kind of the theory behind that. And believe it or not, macro op fusion is actually used in x86 architectures too. So for example, if you do something like push EAX and then execute return, for example, that will execute in a single cycle because they recognize that operation. If you execute a compare instruction and then a jump if 0 or jump if equal or whatever, that is also a single clock instruction now. So here are some macro op fusion examples as I see it. And again, this has not actually been implemented. But if we look here, I have this 1 underline, 2 underline, 1 underline, 2 underline. That's intended to help you visualize what gets executed in what cycle. So here we have one cycle where we fetch or we set the register address given. Normally that would consume 2 cycles. RF fetch, of course, is the third. We can't really go beyond that because we don't have the data yet. But once we have the data, we can take 1, 2, 3, 4 here, our numeric constant, add it, and at the same time, push the destination register constant onto the data stack. So what the instruction decoder sees here is normally the sum will be put at the top of stack, but because it recognizes that it can compound on top of this instruction, it'll put it in the second top of stack instead. And then it will actually just hardwire the top of stack to that value. So in a single clock, we can actually add and push a literal at the same time. And then finally, we do our register store and we fetch our next instruction in the last cycle. So here we have an add instruction that takes 4 clock cycles to execute, which now puts us outside of the speed boundaries of TMS 9900 and well into the boundaries of Motorola 68000, which is significantly faster by at least a factor of 3. Subroutine calls, same thing. We actually have 1 cycle to fetch the PC, 1 cycle to set the destination register, and then notice here again we have PC fetch, a literal, and an add. So at this point we're just adding 2 numbers and we're pushing ultimately 1 item onto the stack. And then in the 4th cycle we consume that with PC store and then we commence the next instruction fetch. And remember that our most sophisticated instruction took 13 cycles previously. Here, as you can see, we actually are now taking only 6 cycles. So it basically doubles the performance of what used to take a fairly long amount of time. So on average, if we were to add all this up, throughput is around, if you did floor division, it comes out to around 4-ish cycles per on average. But in the worst case as presented, it's 6 cycles, which is still demonstrably faster than the CPU found in a Texas Instruments, for example. So the combination of customized instructions plus macro op fusion allows us to get an average performance that is very close to a Motorola 68000 or 68010 in some cases. And actually, when you think about it, the average instruction latency on a 68000 falls between 8 and 16 cycles, because especially if you're accessing external memory or using indirect addressing modes with pre or post increment or decrement, we're looking at somewhere in the vicinity of 12. So it's possible that this can actually be up to 50% faster than your 68000. So where am I with this so far? So I did develop the S64X7 MISC core, as I said. That is known to simulate correctly. I haven't actually fabbed it onto or synthesized it onto an FPGA yet. And I likely won't in the immediate future, although I may consider revisiting the Kestrel 2 with this new architecture. Let's see here. So I have the GitHub link there. And basically, it's actually my first true fourth CPU, 64-bit wide stacks, address bus, and data path, 6 deep data stack, 5 deep return stack, but it is hampered by executing only 1 instruction per clock. I never thought I would say that because there was a time when that was the cutting edge in CPU performance. But without macro op fusion, it's still not performant enough to be useful for my application. But the real reason why I'm not continuing with this is I never got far enough to implement macro op fusion because it's still too big for the FPGA that I want to target. I could easily implement this on a Xilinx FPGA. Even the smallest FPGAs from Xilinx today are absolutely gigantic compared to the ICE40s. But since I'm specifically targeting the ICE40s, I want it to be somewhere in the vicinity of 2,000 lookup tables instead of 6,200 like what I discovered it to be. So while it's too big to fit in the 4K ICE40s, it's at least small enough to fit inside an 8K device, which is nice. So the conclusion is, can you use MISC to implement a RISC? Yes, absolutely. There's no question about that. Will it be small enough to fit in a reasonable sized FPGA? Unless you're talking about the absolute smallest possible on the market, yes, it will actually work or fit quite well. But like I said, it does not fit in a 4K device, whereas it will fit on an 8K device, which is kind of halfway to where I wanted it to be. And finally, yes, it will fit in a Xilinx FPGA. But honestly, in order to implement all that complexity with macro op fusion and stuff, if you really wanted to do that, the Xilinx FPGAs are actually big enough to support a true 5-stage instruction pipeline, at which point you'll get 1 RISC-V instruction per clock throughput, as distinct from 4, which most of your open source designs are. And that's my current report. Cool. Any questions?
Well, more enough, I was looking up the open RISC, and yes, the guy who did it for the Google Summer Code. So I'm thinking, wow, you get G-port, running our tabs are running on your chip here.
Mm-hmm. Yeah. If you can target the S64X7, it does, like I said, there are some things that it needs. So the S64X7 is just the MISC core. It's not the RISC-V pre-decode or anything like that. Those things can be added later on. But if you could target just the S64X7 as is, if you add support for interrupts and different operating modes like user mode, supervisor mode, and stuff, all of which are very easy to add. The only reason I didn't do it is because I just didn't need it. But if you target that, like, you could have a complete, stack. Yes. Yeah, and that's.
And be able to see the nice thing. One of my goals is to be able to have
Yeah.
So that you can actually go click in step and actually say, okay, what's the, what is the state of the pools? What's the current priority? How much tick do I have left if I'm running
How much quantum? Yeah.
round robin?
Right.
Stuff like that.
Yeah. So the comment was recognizing the opportunity to port RTEMS with which itself is running G-Forth, and have that stack running on top of the S64X7, suitably modified to include privilege levels, memory management unit, and there's something interrupts and traps and things like that. So yeah, that's definitely a very real possibility. But like I said, the S64X7 as it exists today is still just, it's very crude, very minimal. Needs some TLC in order to get that into a more professional package. But it is definitely doable, and is, like I said, it is 64-bit.
But that's what I'm saying also, because USB is really starting to become big, is to be able to have like a general purpose, put whatever application you want on there, so that you can just plug this into a development computer that you actually use as your display.
Mhm.
It's not, remember, port is self-contained. So you'll be able to do all this stuff you're going to be working on will be on the hub itself.
Right.
Which means you need to plug in whatever peripheral you want.
Mhm. Yeah. Yeah, and like I said, I'm thinking of revising the Kestrel 2 to switch from the 16-bit CPU to the 64-bit CPU. But before I do that, I have to renovate all the build tools, because right now they're all targeting the 16-bit MISC core. Cool. The goal is for this November. I don't know if I'll achieve that, but we'll see. I have a new development technique. I'm going to go back to trying the 6502 style PLA for instruction decoding. But I have a tool that I wrote which converts a set of state tables that I express in a more tabular format, which is wonderful for keeping your mind, like you could see everything. It's like the map may not be the territory, but damn, it's awfully close for when used in this particular application. And it takes that to or an invert logic in Verilog. There's no case statements that it uses. It's all literally wire X equals Y and B and Z, or A and B and not C. Like it has this logical chain. And I've found that if I do that, it actually reduces this number. Not only is it more convenient for me to implement using this tabular format, but it actually turns out that it reduces the number of resources used on the FPGA. Because when you use a case statement, for example, to decode instructions, it's not rendering just a bunch of AND gates to recognize the inputs. It's actually instantiating a priority encoder, which it has its uses, but it's not appropriate for this particular application. Unfortunately, Verilog doesn't offer a correspondingly simple syntax for generating just what I need, a multi-hot state machine decoder, basically. So there's that. The other thing is the multi-hotness that I just mentioned. With a case statement, you have one and only one output that fires based on your inputs, which makes sense. I mean, that's what a case statement is for. But when you're trying to minimize logic and you're trying to reuse the same amount of the same PLA terms across multiple classes of instructions, it doesn't quite work out that way. What ends up happening is in order to really do that, you have to break these out into separate case clauses, and you end up with related logic that is widely scattered throughout the Verilog source, and just trying to keep track. That's actually what killed me the first 3 times, was just trying to keep track. Okay, did I or did I not set this term? And if I did, am I driving this signal from multiple locations, which happened quite a bit. And just trying to rectify that I guess the official term is trying to get design closure on that is very difficult to impossible. So at least with the tools that I have and the experience that I have. So by writing this tool, I'm capable of having multi-hot outputs expressed in a very compact form factor. And that allows me to see, because there's, realistically speaking, there's only like 24 or so instructions that I need to explicitly decode in RISC-V. And that's it. So this should have been trivially simple for me. I mean, my MISC core has double that number of instructions easily. But, you know, it's because it's all widely separated and stuff. I just couldn't wrap my head around it. Now I've got the state tables. The logic actually works. I have reason to believe, I haven't tested this yet, but I have reason to believe that the logic is small enough now that I can actually put a 64-bit to 16-bit bus adapter on the CPU so that I can actually drive the external bus pins. Whereas with the MISC that I have now, the S64X7, it is so large that I don't think I can fit a bus bridge on the same chip. I would have to dedicate all possible I/O basically to driving an external bus, and that will suck. Basically, it would be very difficult. Cool. Any other questions?
How about just build the MISC core and let the software
The emulation. So the question was, why not use the S64X7 alone and just let the software decode basically as like a hot, or basically as a CPU emulator as a stopgap measure. That was actually my original plan for the MISC, to start off very simple and just kind of build up from there. And then as I added hardware features, I would remove the corresponding software features. So there's always that parity there. But again, the MISC is taking up so much space that I don't know if I can fit the bus bridge on it. And that's the only thing that worries me. But if I can do it, then I'll definitely give it a shot. I mean, I've still got, what, a month and a half or so to go before I reach a critical point. So I'll play around with it. But right now, because this tool allows me to so compactly represent these state diagrams, I'm basically going back to the 6502 approach and just seeing, like, how does this compare with my original 6502 approach? Like, what's the difference? What can I learn from it? You know, that, is it too small? Is it, or I'm sorry, is it too large? You know, because if the size of the project is about the same as the MISC that I have now, then it makes sense to go back and use the MISC to software emulate, because it's already proven. But if it proves to be smaller and more amenable to that 16-bit bus, which is a bottleneck, I understand, but unfortunately that's what I have to work with, then I'll probably pursue that and debug that instead. Just out of, I need to get this done soon, because November's around the corner. Mm-hmm.
And then just give it some room, 8 bits
Mm-hmm.
For an instruction. And if you have a 64-bit machine, and every time you get 64 bits,
Mm-hmm.
8 instructions. And I think you can probably emulate all the disk instructions. All disk instructions with 8 MISC instructions. And then, you know, if you just organize the pipeline properly, then, you know, you just take how many stages of actions. If it doesn't need 8 stages, it will terminate the instruction
after all the work's done.
Mhm.
Most stages are whatever.
Yeah.
You probably will waste memory space, but I think audio-wise, it's probably better.
Yeah. It's hard to summarize for the internet folks what was just said. Basically, doing the S64X7 emulation, most of the RISC instructions can be emulated with the 8 MISC instructions. Yes. In fact, to a large extent, or I should say mostly, the CSR set of instructions, those take up around 12 or so. So I will have to split that up into two separate words, but easily 99% of the instructions take actually less than about 5, based on my research. So basically, like I said, between 64 and 128 from the instruction fetch to stack op decode, and then from there to the fetch unit, the MISC unit rather. But most instructions will fit in 64 bits for sure, absolutely. And then you combine that with macro op fusion, and we can actually get that down to literally 4 cycles, if not faster. But those damn CSR instructions are just a thorn in my side. They are, I don't know what it is about RISC processor vendors, but they always got to throw in that one class of instructions that's like ridiculous, that just blows the architectural elegance of the architecture out of the water. And the CSR instructions for the RISC-V are the ones that do that. But at least it's finite. You know, at least I can say, okay, this fits in 128 bits, guaranteed. You know, I don't need any more or less, and that would be ideal. That would definitely be ideal for a hardware implementation. Yep. Cool. Yes.
Are you planning to post or email your presentation text to the website?
Yes, it is just a plain text file because I wrote it here.
I like that.
Yes. Yes. Fresh off the mint.
Want to go crazy with it, make a PDF out of it.
Yeah, exactly. I'll typeset it.
You know Dave well. There you go.
I'll typeset it in LaTeX.
Oh man, awesome.
That's still LaTeX. That's still LaTeX.
Yeah, it's still LaTeX, but
Yeah.
it's, what you see is what you need.
Right.
Did my thesis use that.
Yes. My data sheet for the S16X4 is written with that tool. Cool. Well, thank you very much. And
Commodore 64 in no time.
what's that?
Said, wow, Commodore 64 again in no time.
Well, yeah, maybe.
So basically, that's it, right? That's the last one.
Pick up after yourself. If you haven't put money in the kitty,
Please.
I would still rather someone else have the see you next one.
What's that?
Say, we'll see you next one.
Oh, yeah.
together for your
So,
awesome-
all right. So everybody on the internet, we're going to sign off here because I was the last presentation. So I guess we'll see you next month, hopefully, if we can figure out some. Yeah. So just stay tuned to the SVFIG mailing list. If/when we figure it out, we'll definitely post our results there. So cool. I'll see you guys next month.